that we went through that what are the steps are there for a common water treatment system for both your surface water and groundwater. Groundwater, some irrigation, some parts are also included there. Okay, so that one of the common process that actually is your this fluid that we goes through is that the sedimentation, right? So sedimentation chamber is like this. This is some kind of sedimentation chamber from where the water actually is flowing there. And you have there are slips are there of different sizes are there. And these slips that will, when it is passing through the sedimentation chamber, it will be sedimented at the bottom of the slab, and from that you can actually take it out. It's for the sedimentation. You can understand that we can input this forces means that when these slips are inside this one, just only the vertical forces if you are considering. Otherwise, the horizontal direction flow is that whatever the sediment are there, they are actually flowing with the water flow, right? So whatever the water flow velocity in the chamber, they are following that. And here that settling velocity, that is following, that can be found out by balancing out these three forces, these two forces. One is the buoyancy force and the drag force, and the other one is gravitational force. So I think you don't have many trouble identifying it. Okay, identifying it. The first one is that your drag force is given by the Stokes law, and for any slips you can consider that effective diameter, right? And from there you can find out the Stokes law and what is the drag force that acts on it. And for the other gravitational force, of course, we need to know what is the density of the density as well as the volume. Volume is the diameter, effective diameter. If you know what is the volume there. And similarly, that if you know the volume of this your particle, then you can find out how much this water it will be going to be displaced, and from there you can find out what is the buoyancy force. That's and once you balancing it out, then it's giving the Vs. That is what you want here is Vs, and once this is known, then you can find out that what should be the basin diameter, right? Effective basin diameter for a given flow velocity, right? For a given flow velocity, and also your cross sections, right? So the first step, you see that is HT is that for any general case, it is given that for your settling velocity, right? So it is going in there as well here. The particles which is starting from here, the slips is starting from here, and if the slips you are just keeping it here, then it will be reading, it will be just suspended, sorry, it will be going to the bottom from some distance. But as it has now a horizontal velocity, so therefore this one is actually moving, and you find out that from this side to that end, which is a length of what L. Let's say it is this length is given by L. Right. So then what is the time it does it take from reach from one to another end? That is given by your this velocity. So if it is F is the flow velocity, then L by that is theta, and from there then theta. If it is your cross section is AB. So if the cross section is AB. then water presented, then presented the last portion. And this is your volume, the sedimentation, this chamber, air into heavy and volumetric flow, like with which it is actually moving towards it. Right, and from there you can find it on this at this type, that how much is it your suspension. Right? This is actually going into the bottom, and that is given by the VS theta. It is actually replaced here. So you means that for this given diagram which is shown here, means that HP, you can see that the HP is actually less than H. Means that what? That for this one, the slips are actually not going to be collected at the bottom, rather it will be flows out with the this water flow, right? So therefore you will be having settling velocity, right? Or critical settling velocity, and the critical settling velocity that should be higher than the given settling velocity, so that it will be collected at the bottom, right? And you can see that. Then you can find it out by the depth of the sedimentation chamber, and that's it. Okay. Right. So related simple this I have just pasted here from the book itself. I can see it like what is it giving? A drinking water treatment plant uses a circular sedimentation basin to treat 3 million gallons per day. Right? And after storms occur upstream, the river often carries this 0.01 millimeter particles with the average density of this. Okay. And the slip must be removed before the water can be used. Okay. The plant's clarifier is 3.5 meter deep and 21 meter in diameter. Right, and it is at 15 degrees centigrade. Right, so what is the first thing is that what is the hydraulic detention time of the clarifier? Right, is that what is the time it should take to detain all this the slips? Okay. So hydraulic detention time, you see that it is a cylindrical and circular sedimentation basin. Right. It is always that's why the reason is that theta that was actually defined by this V by Q. So that gives you any shape actually if you can find it out. And therefore I can see that what is the first thing is that hydraulic detention time of flow through vessel is V by Q, where V is always your gaseous volume, Q is the volumetric flow. So what is the for this if it is a 3.5 meter deep, right, is actually a cylinder, right? It's a cylinder. So therefore the V you know, from there the V you can find it out. And the other thing is that Q is also given it here. The what is Q? MGD, right? 3 MGD. From 3 MGD, from there, if you want, then meter cube per second, which is the volumetric flow rate, right? So from there, the theta part that I can find it out, and after that, what are the rest? What is given in here? That the theta is given by 2.6 hours, right? So it will be taking us 2.6 hours for this volumetric flow rate to completely get it. What is the sedimentation time? It shows it here, right? Hydraulic detention time. Then next part is that will the clarifier remove all of the slip particles from the river water, right? So here you need to find out for this given sedimentation basin, which is a cylindrical in type, that what is the critical settling velocity. if your critical, this settling velocity, what is, you can find it out, if the settling velocity is greater than critical settling velocity, it will be completely remove these particles, otherwise it won't be able to do it, right? So that means that you can, since you have your this dimension type, you will find it out. So from there you can find out what is the your VS. The VS formula is already given. Right, so from there, because rest of the things are given, the dP is given, the particle diameter, right? Particle diameter, so water is at 15 degrees centigrade, so you know what is the water density you need to take, and also the slips density, right? That is also given. So from there, you can find out what is the critical velocity, right? And what settling velocity. And yes, see, it has 2.6 gram per centimeter, and from the table you can find out what is the water, which is given by 991 kg per meter cube. And from there you see that your settling velocity 5.74 minus 5 meter per second. Whereas your critical density is given by if your depth is h, right, so the critical density is given by h by theta, right? Right? So h by theta, that is what you can utilize, or you can utilize q by l, whatever, but it is not, in a sense, it is not given there, right? So therefore here the best is to use the depth by the theta, detention time, right? So h by theta, then you find out that what is the critical velocity, which is given by 30.10⁻⁵ meter per second. Means that your settling velocity is much lower than your this critical settling velocity. So therefore, all these slates won't be able to be removed by this clarifier.
Sir, how is viscosity calculated? Mu. How is it calculated here? Like 18 into 10 into 10. Where do we get it from? In VS expression.
This we don't have right here.
So the value
Oh,
of
mu, that will be viscosity, that will be given in water. That is given, that we don't have to calculate here. So here you see that this is 0.0014, that is given. It's a water medium. So the water medium you have to find out, not this air medium which is on. Okay, so I think this, you can got this, what is the idea of sedimentation chamber. The next one is your coagulation and flocculation, right? So coagulation, flocculation, one of them is, the first one is a chemical process and the flocculation is a physical process. So coagulation is coagulate and there are suspended colloidal particles will be there. So that will coagulate and make it bigger there. And the other one is that your flocculation, that you can make a very mild agitations mildly, so that these actually the particles that come together, and therefore after that they can be make a aggregate and bigger particles are there. So that from there the filtration, it can be done better in the next step. So the coagulation is actually takes care of these properties of this coagulant. One of these coagulant that you can see it is given by this alum. So what happens that it can actually help in two ways. The first thing is that your, in general, like these suspended particles, they will be having net negative charges there, right? So that is one of the reason actually when the net negative charges are there, they cannot actually join each other. Right. So whenever they are suspending, they are coming to near to each other, they will be repelling each other. Right. So this coagulant, when you add it, we actually release this, like because it is positive ions are there. So Al3 in that case, you can see that, and this actually neutralize this particles. Right. So in the surface charges they neutralize, and therefore they can help them actually to bring together and coagulate them. Other thing is that when you mix this alum in the water, then it can actually make this precipitate of this aluminium hydroxide, right? Aluminium hydroxide. So this you can see that it actually makes a light fluffy flock, right, which will be absorbs the suspended particles together, and they can all together they will be making it aggregate particles there. Okay, so that is the like a two-way these two process by which this can be which was earlier stabilized particles, they can aggregate by colliding with each other. Colliding with each other because that is how you actually efficient. Means that when they have to come to each other, that is when they are touching each other, that is a collision you can consider. So one collisions, then if that collision is like if every collision is successful, and these two particles when they are colliding each other, if they are making an aggregate particle, so which means that the collision efficiency factor alpha that you can define, and alpha will be equal to 1, right? Means that every collisions that make an aggregate particle. If like the probability is like that only one in every 4 collisions it is there, so therefore you have your efficiency is 0.25. Okay. Right, so this can be in fact, but other thing is also defined like that alpha, right? Right, so next one is that your flocculation chamber. So flocculation chamber, you can see that there is this after this operation it goes to the flocculation chamber, and there is this mixer is all fully mixed there. Then there is flocculators which is given there. So it is like a pattern, right? And you have to go like a step by step. Like you have a multiple chambers are there, one by one you can see that. And what happens that you have make some agitation there, gentle agitation. So then this precipitating this aluminum hydroxide is starts to form a plainly visible flock, right? Which was like a suspended at pieces. Now that with these agitations, they will start making it together. Okay. It has to be maintained in a optimal way so that it is sufficient to encourage particles to make contact with each other. But when it is going inside, it should not make break. Okay. So therefore, it should not be that much vigorous that the fragile particles break apart. Now, this factor, this is called the mixing intensity. So mixing intensity is that given, right? I mean, I have not derived it or not, it is given here, but you can see that it depends upon proportional to the P. Means that the power you are given to the saddles. Okay. So the power that is given to the saddles depends upon that, and the inverse proportional to VB, right? So VB is the volume of the vessel, and U is the viscosity of the water. So mixing intensity depends on this P and mu and VB. Okay. All right. Yes. So now, what is how do you quantify the aggregation, right? So G is the one which is like your mixing power, right? So you are giving saddle how much you are giving, that is the mixing intensity, how well it is mixing there, right? So the first thing is that we can think of it is the mixing is so well that we can think of it as a CSK, right? So it is a uniformly, continuously stacked and reacted, and uniformly like a mixture. Right, and the effluent number concentration from one chamber being the influent number concentration for the next chamber. Alright, so whatever is like a leaving here, it is now it is going to the next chamber. Right, so what actually you are observing, you are monitoring, right? Say the suspended particles that you are actually checking there. So suspended particles, you can count that per unit say volume, right, per unit water volume, this much suspended particles, that you can always observe, right? Take a sample and you can find it out, right? So now when you are actually flocculating, right, flocculating, then what happens then? The number of particles that increases or decreases. Okay, so it will be aggregating, it is decreasing, right? So it is decreasing. Total volume of the particles doesn't decrease, right? Total full total volume. But the thing is that this thing is actually the number of particles which was suspended, it is decreasing. Now the decreasing, then what is actually, there are some reaction, like CSTR when you are considered, remember that. So there is some kind of reaction that is going on, or you can consider that, yes, let me consider this as some kind of reaction, although it's a physical process, right? Always say, not a reaction means always we think chemical process, but it's a physical process. So for some assumption, if it is mild agitation, right? If all the particles are initially nearly the same size, the water mixing is relatively mild, and the aggregates volume is the sum of the volumes of the individual particles comprising the aggregate, right? So I think it may just not very complicated thing is there. So therefore, you can consider this process as a first order process. Okay. So first order process that you can consider, and simply therefore these reactions dN by dt, right, which is a decreasing. Right. Okay. First order reactions you can consider where K is given by this alpha colliding factor, depends upon the colliding colliding factor, and your omega is that and the G, the mixing efficiency, right? Depends upon the fluctuations, because that is how it will be depending, right? And omega, which is nothing but the volume of the flow, right? Okay, which is given by this N0 is your initial number concentration of the monodisperse particles of the diameter B. So, and we are considering that it would be aggregate volume will be actually the same. So when you are adding up it is going to be same, right? So you are this chamber, population chamber is there. Right, so any population chamber is there, and here your this effluent is going in with some volumetric flow rate, right? Okay, and say initially for any population number, say initially it is N0, okay, N0, and here your CSTR, so therefore when it is coming out with also Q, but N, okay, and you are having in this population chamber a first order reaction, but a physical thing, okay, it's a physical thing. So first order reactions we used to do it by like this, right? AC is like this, if it is an E is the, if you use your total volume, right? Let's stay here. Okay, so but here what you can write instead of this C, which was the concentrations, mass concentrations, here the thing is that you are monitoring N. So there you can make it as a N, right? And what you can do, you can write it as a given 0. Okay. Right? K is, you can, it is given by this formula K here. And you can find out what is your N0 by right, N0 by N, which is given by 1 plus alright. Okay. And if it is, you have to repeat it for multiple flocculations chamber, right? So then again this will be for the next one. This will be your initial N. Then you can find out N how much is there, right? And you can find out that by this completely taking the ratio at the end, N0 by N, that how much it is able to make it aggregation. Okay. Right, so please go through these some examples given here, not very difficult things. Okay. Yeah. Okay. Right, so this is the population. So here is our, let us see this last topic, filtration. Okay. Filtration is exactly not like a straining. Okay, I mean it is a filtration, but it's not exactly like a sieve filter. It works in a multiple way, and you have your water filter in your room somewhere. I mean in your home, somewhere in your hostel. And the thing is that it's not exactly the some materials you are going to use it, like some material, but it's not exactly always straining. I mean, straining is not or straining or sieving. Means that there are big particles are there, and you just make it. Just take them in your this medium, and the only the clean water is coming in there. So there is like it's all kind of process actually going in there, but it is the most effective means of removing small particles, and not only that, small particles, it can make it a take out of the pathogens which are like a very, it would be very small there. What happens there, it can actually go through a different process, and this is all the most popular one is called the rapid depth filtration. So rapid depth filter consists of a layers of different first thing is sieving intermediate such as sands are there, then I then this dialysis are, and a bit of wetted wheat and drop of a bit of wetted granules. And filtration is accomplished by, of course, straining is there. Then there is like when it goes through there, by means that there is a continuum. Populations will also goes in there, and there will be like sedimentation in the more species. That is also important removal mechanism. So it can also be like when it goes through there, there is a like sedimentation process that can also be there. All right. So your this filtration rate is given by Q by A. You can understand that this is a unit of velocity, right? Filtration rate, where your Q is the volumetric flow rate, and A is your filtration cross section area. Okay. So filtration, this cross section area, you industrial process, right? The municipality, that you need to make it a faster, right? And this cannot be like a more than 100 meters square like that. Okay. So to treat like a large amount of water, what you need to do, you need to make a multiple filters. right? Multiple filters are together so that it can see like a very large one. And you can have a huge number of volumetric flow rate, you can treat it like this, okay? So in that process, what happens that your filters, when you are continuously using, it gets actually clogged also. Right? The medium gets clogged. Different mediums are there, multiple layer or layers of this medium is there. Right? It has a different words is there. I'm not going to explain this all these things. But now the thing is that when it is a continuously running, it has to be like 24 hours. It has to be run, right? So what they do actually is a sections of filters are there. So all the sections, it is unlikely that everything will be clogged together. Okay. So what you can do, you can take some water from this side, like some part of the water, and it can passes through again here, which is called the backwashing. Right? You can take it as a backwashing, and backwashing and as well as also rinsing. Make it and rinsing by some process there, rinsing process. So means that part of the water is actually utilized in the filter backwashing and the rinsing there. So your effective this filtration rate that will be changed like that. And this is given like you can consider this process. So your VF is the volume of water that is filtered per cycle per meter cube, and VB is that one you have to subtract it, and as well as VR, which is the volume of the water which is used for the backwash as well as the pure rinsing, right? And the other part is that what are the durations for taken for this thing, and from there this is what you can find out filter efficiency, which means that the VF from your cross-sectional area and your rate of flow, what you can find out that much water it was supposed to actually filter it out, but this much part is actually utilized there. So that is your effective filter efficiency. And for their effective filtration rate also, if you have the idea of the time, you can find it out also. That how much volumetric flow rate is actually there. Just a subtraction. Okay. Right. So let us stop it here. This class. So I haven't discussed many things actually. In fact, right? Like disinfection, that was the last part is there. But disinfection is like that very, we have discussed this common disinfection medium is that you can use chlorine. You are aware of this chlorine, right? Now there are like it depends upon that what kind of like pathogens are there. So in that way, sometimes something is not effective, something is ineffective. So if possible, I will do that. I will add with these slides. Just this, as the information, I will put all this as an extra slide. I will put that. So that is your syllabus. Okay, your syllabus is up to this part. The other this what are this treatment part that we are not discussing there. For example, that how the water hardness alkalinity that is maintained, how the water softening, etc. Or for the groundwater, this treatment actually. When that is okay. How we have discussed it now. Now, this major, what Professor Satya discussed, like 40 marks was there for meat, right? So that was the meat, and 40 was for the your end cell. Yeah, that is what it was there. And 15 and was quick. So it was surprised that I announced it. And 5 for your assignment, right? So I have evaluated the quiz 1, the quiz 2, 3. We evaluated. I will call you in between, like by Friday. You can call it to be in the lab. You can check your answer, these copies, right? So that I can announce the PMT, right? And what I will do here, you do the checking. What I will do that I will scale it. Okay. So that is I think when it is announced, right? So I will scale it. So your NSEM will be in the 40 marks. Okay. 40 marks. Now One thing can be done, we can 40 marks total, we can keep it whatever I discuss, or if you want, I can give 5-10 marks from the this. I mean, that is the in general rule is like that. Some part should be based same exam, right? So, anyway, two faculty members are taking, so that is little absurd actually. So what we'll do, we'll keep it whatever I have discussed. So 40 marks is there, right? It will be, your questions will be both conceptual and numerical. Keep it in mind, okay? It's not like that, I don't keep fully numerical. Okay, so maybe 50-50, maybe 60-40, numerical 60-40, something like that. In general, I keep like that some topics, some conceptual questions, followed by numericals related to that. In general, and by this time, you are able to identify what are the topics I have discussed, right? Okay, that is it. All right. I think anything else? Any more? Formula sheet, what formula sheet you want? That is not enough formula. These are, it is so basic, but you should be ashamed like that. Why are they doing this formula sheet? Right? So, the only mass balance, right? See, in general, just stop it, okay? So, where you feel like formula sheets are given, like in whatever we have discussed, you see that even today's class also is the mass balance equations there. So, mass balance equations, then what is there? Anything other formula sheets I generally won't giving like this. For example, you may not have to remember these Gaussian Bloom equations, all these things, right? Okay, right? Okay, got it. Up to now, whenever I took this course, I have given this formula. So that is what I provide like that. Okay. So, but this electrostatic precipitator, these are so very basic. So that is what you should remember, right? Okay. That is the thing you should remember, right? Otherwise, I don't see, except that Gaussian Bloom equation, I don't remember that anything else is there, not much in that. Right, but you see that even the river flow, etc., that this oxygen sagging curve, those parts also you can start from the basic. I won't ask you that ये फॉर्मूला है आप यहाँ पर नंबर ये लगाओ नंबर लगाओ और बताओ कि मेरा कितना डिप्लेशन है, what is the DO? I won't give such type of question. The question will be like that. If the numericals are there, you have to derive it. So the basic principle you derive it, and अपने आप को derive हो जाएगा, you can give it like that. Understand? Alright. So don't worry. Aarti Singh, Saloni, Naina,